Now that we've considered the formation of hybrid orbitals, we now want to consider how we use these hybrid orbitals to form bonds, whether they be carbon-hydrogen bonds or carbon-carbon bonds. Okay, so if an sp(x) orbital on a carbon atom overlaps with an s orbital on a hydrogen, or another sp(x) orbital on another carbon atom, for example, a sigma bond forms. Sigma bonds are defined as being cylindrically symmetrical with respect to the interatomic axis. And this model set does a good job of describing what a sigma bond looks like. So we've got a carbon atom, we've got a hydrogen atom, and the electrons in the bond between them are completely located within the cylinder defined by the two atoms. So if I look at this bond on end, you can see the hydrogen atom, you can see the carbon atom, but you don't see any bonding electrons protruding above or below this axis. You will just see the hydrogen atom in front of you, the carbon atom behind you, and all the bonding electrons are along that axis. Okay, so let's see what this looks like when we want to make methane. So in making methane, the 4 sp3 orbitals on the carbon atom overlap with the s orbitals on each of the 4 hydrogen atoms to give 4 carbon-hydrogen sigma bonds. Okay, so on the left here, we have the sp3 orbitals and the s orbitals. And then when we actually allow those hydrogens to come closer together, you can see the sigma bonds that are formed from the overlap of those hybrid orbitals. You need to be aware of the fact that only orbitals of the same symmetry type can overlap to form bonds. Well, what do I mean by symmetry type? That's actually a mathematically rigorous concept that for people who go on and become chemistry majors, you will investigate this in more detail in physical chemistry or inorganic chemistry classes. But for the moment, the best example to give for the purposes of this course is that you cannot try to overlap an s orbital or even an sp(x) hybrid orbital with a p orbital. An s orbital is spherically symmetric. A p orbital is dumbbell shaped. It is, red on one side and blue on the other, shaded on the top, unshaded on the bottom, or other ways that that's depicted. What that is saying is mathematically the sign of the wave function is positive on one lobe and negative on the other lobe, and that simply cannot be mathematically combined with a spherical s orbital or a cylindrical sp3 hybrid orbital. So be careful of that. You can form sigma bonds from sp(x)s and from s's, but you cannot actually use p orbitals to form sigma bonds. Okay, so we want to take this one step further. We talked about methane. Now we want to make this a little bit bigger and talk about ethane. Well, ethane is the molecule C2H6. Each carbon is bound to 3 hydrogens and the other carbon. So the carbon-carbon bond in the center of this molecule is formed by the overlap of an sp3 orbital on each carbon atom. The carbon-hydrogen bonds, sigma bonds, are the same as in methane. They are formed by the overlap of an sp3 orbital on carbon with an s orbital on hydrogen. Okay, so in this molecule you get to see both kinds of overlaps that give rise to sigma bonds. The overlap between an sp3 and an s to form the CH bond, and the overlap between an sp3 and another sp3 to form the carbon-carbon bond. Taking it one step further now, we can talk about how we get double bonds. Okay, ethylene C2H4 being the simplest example of a molecule that has a carbon-carbon double bond. The sigma bonding is going to be exactly the same as in ethane. except that instead of using sp3 orbitals on carbon, we're using sp2 orbitals on carbon because the carbon is sp2 hybridized. Okay, so the carbon-carbon bond is formed through the overlap of sp2 orbitals, and the 4 carbon-hydrogen bonds are formed through the overlap between an sp2 orbital and the s orbital on hydrogen. What is left behind is a p orbital on each carbon atom, and as we're going to see, those p orbitals can overlap with each other to form what's called a pi bond. Okay, so what's the definition of a pi bond? A pi bond is a bond that has its electron density above and below the interatomic axis. Okay, so if we try to look at a model of ethylene, and you look at the carbon-carbon bond axis here, you can see in this model in particular that there is electron density above and below the interatomic axis. And that is due to the fact that this molecule has a pi bond. This should make sense to you, okay? So the double bond consists of 1 sigma bond and 1 pi bond. We already have the sigma bond between the 2 carbons from the overlap of the 2 sp2 orbitals. The overlap of the 2 p orbitals gives us a pi bond, and it would make sense that those electrons need to be somewhere else. Remember, when we discussed VSEPR theory, we said that electrons don't like each other very much, and you don't want to have more electrons in the same region of space than you need to. Well, if you're going to have a double bond, there are going to be 4 electrons between 2 atoms. It is best to put 2 of them directly in between the 2 atoms, and then have the other 2 electrons above and below the 2 atoms. So those additional electrons have the opportunity to go somewhere else in space. Okay, when we are overlapping lobes, we need to be very careful that we can only overlap lobes with the same phase. Mathematically speaking, that means the same sign of the wave function when we're forming pi bonds. I take a more pictorial approach and a less mathematical approach towards these subjects in teaching organic chemistry. So I like these pictures here that have one lobe colored red and the other lobe colored blue. The lobe colored red, we say, has a positive phase. The lobe colored blue has a negative phase. And as you can see from the picture, we can overlap red with red. We can overlap red with blue. We have to overlap the red and the blue in order to successfully get a pi bond. You could not take one of these p orbitals, put them upside down, and try to overlap red with blue. That would not give a bond. Okay, what happens when we try to move to the triple bond? Okay, so in acetylene, when we have a triple bond, the triple bond consists of 1 sigma bond and 2 pi bonds. So the sigma bond consists of the overlap of an sp hybrid on one carbon with the sp hybrid on another carbon. The second sp hybrid on each carbon can overlap with the hydrogen atom on that particular carbon, but that leaves 2 p orbitals left over, one vertical and one horizontal, and those p orbitals can overlap with each other to form 2 pi bonds. Okay, so a triple bond consists of 1 sigma bond and 2 pi bonds, and the pi bonds are mutually perpendicular to each other. So for the vertical pi bond, red overlaps with red, blue overlaps with blue. For the horizontal pi bond, red overlaps with red, blue overlaps with blue. Okay, and those pi bonds, of course, are formed through the overlap of the px and the py orbitals on each carbon atom, assuming that the interatomic axis is the z-axis, which is how we typically define it. Okay, one more thing we need to consider when we're talking about double bonds and triple bonds are bond lengths and bond strengths. And this is best looked at by looking at a table. Single bonds are longer than double bonds, are longer than triple bonds. And that should make sense to you, right? Because the way to think about this is that if you have more electron density between two carbon nuclei, that's more glue, so to speak, to hold those two nuclei together. So in a single bond, the carbon-carbon bond length is always 1.54 angstroms. An angstrom is 10 to the negative 10th meters. And its symbol is an A with a little circle on top of it. A double bond has a length of 1.34 angstroms, and a triple bond has a length of 1.20 angstroms. Okay, these numbers have been carefully discovered experimentally and verified again and again and again through a technique known as X-ray crystallography. What is more interesting than lengths are bond energies. Okay, so a carbon-carbon single bond has a bond dissociation energy of 368 kilojoules per mole. So what that means is you would have to dump that much energy into this molecule to cause the carbon-carbon single bond to break apart. Now, a double bond contains two bonds, and you may think that it would take twice as much energy to break a double bond as it does to break a single bond, but that turns out not to be true. The bond dissociation energy of the double bond is 632 kilojoules per mole, and it's only 1.7 times as strong as a single bond, not a full 2 times as strong. So if we assume that a sigma bond has a strength of 368 kilojoules per mole, what that means is that a pi bond only has a bond strength of 264 kilojoules per mole. The fact that it's easier to break a pi bond than to break a sigma bond is something that will actually show up again and again when you consider the reactions of organic molecules. Finally, the triple bond at 820 kilojoules per mole is only 2.2 times as strong as a single bond. Okay, so in this case, the bond dissociation energy is much less than we would expect for 3 isolated sigma.